I don't see any changes away from Bayer pattern in the medium term or even long term for image quality or for human consumption. However, on the AI vision side, this is much more interesting because G'day, if you open up your cell phone, you break it down, pull it apart, inside there you'll find a few camera modules. If you then pull those camera modules apart, you'll get down to the image array, a silicon chip based on CMOS technology. That chip has an array of pixels on it. Now a pixel is just one transistor circuit which is sensitive to light. On top of that array, and there can be 100 million of those pixels, is what's called a color filter array. The color filter array acts like a filter. It filters for different colors, hence the term color filter array. And it works in the same way as the human eye does, because inside the eye are things called cones and rods, and cones are the ones that detect different colors by filtering for red, green and blue. So our human eye is sensitive to red, green and blue light, and so this is the way a color filter array also works in these digital still cameras. And it's the pattern of those color filter arrays which defines what is called the Bayer pattern. There are many designs of color filter arrays available today. Some of them do not use red, green and blue. Some of them use red, green, blue and some kind of clear which allows all light in, and that might include infrared light. And then the pattern can be put into different colors, and it's possible to actually make color filter arrays that are not based on red, green and blue. Red, green and blue is a favored color filter array because it matches the eye. And this is where we get to the characteristics of the Bayer pattern which are so compelling. The Bayer pattern was created by Bryce Bayer of Eastman Kodak in the 70s, and it was a patented approach. And it effectively lays out the color filter arrays in a red, green, blue, green pattern. And you'll notice that there's twice as many greens as there are reds and blues. And that's because the human eye is more sensitive to the green light. So it's matching the Bayer pattern with the characteristics of the human eye. And that is very important for generating high quality images. Ones that we perceive as high quality are optimized if we used this kind of Bayer pattern. At the time, Bruce Bayer also created other patterns based around a similar structure, but not using RGB, red, green, blue, but cyan, magenta and yellow. And these have certain advantages over RGB in what's called quantum efficiency. In other words, converting the light energy to electron energy or voltage on the pixel. That would have been useful and would produce better images, especially in low light conditions, but at the time those dyes were not available. Now when we display images, it's required that you have the red, green and blue color elements included for every single pixel. Now, as we said earlier, the Bayer doesn't do that. The Bayer pattern is one color per pixel. So to generate those extra colors for each pixel, we use a thing called demosaicing or interpolation. And there's various algorithms to do that, but essentially all it does is it uses the colors around that particular pixel to interpolate or to render a color for that pixel. After the algorithm, you actually effectively have 3 times the amount of data that is included in the image. So the raw Bayer pattern image comes directly off the image sensor. From there, it can be processed either on chip or off chip, or on camera module and off camera module. Often camera modules have demosaicing algorithms built in, and that has key advantages in that it doesn't need to be post-processed. It can be done directly on the image sensor, and images can come out in direct format for compression, or even directly compressed, JPEG compressed on the camera module. Certain advantages exist also for off-chip processing or post-processing demosaic. It means that photographers or other systems can do a better job or use unique demosaicing algorithms which may perform better in their certain applications. So we have on-chip and off-chip demosaicing, and they have advantages either way. We talked last week about an AI vision system which reduced noise, and they chose to use the raw Bayer pattern images. I would suggest that's because there's much less processing required with the raw Bayer pattern image than there would be for a post-processed, fully demosaiced image. Now, there is no perfect demosaicing algorithm, and they produce artifacts. 2 main artifacts come to mind: false hue and zippering effect. The false hue occurs when there's a boundary or an edge in the image and the interpolation algorithm bleeds color across that boundary. The zipper effect occurs where you get this kind of stepping effect as it moves between pixels and color again is not clearly transitioned across that edge. Now there are better algorithms that continue to be developed, but all demosaicing algorithms generate artifacts. It depends on the scene and the image that it's actually working on. They get better over time, and it just depends largely on the image and the scene that's been recorded. One of the great things that's happened over the last 20 years is the improvement in image size, or the larger cameras, which make these artifacts smaller and smaller, meaning you really have to zoom in to see them. So big images have artifacts which are much smaller and much less noticeable. So is the Bayer pattern going to be around in the future? Well, I think there's two parts to this. There's the image quality part, and that's for human consumption of high quality images. And that's the AI vision part, which is about, can the AI interpret things? So firstly, looking at the image quality part, it doesn't seem to matter to me how many pixels you have. You still want to have good image quality. You still want to be able to zoom in and see details in images. So a Bayer pattern is very good at that, and it's matched to the human eye. I don't see any changes away from Bayer pattern in the medium term or even long term for images that are for image quality or for human consumption. However, on the AI vision side, this is much more interesting because the AI vision systems are there to interpret images. They don't care about image quality. They just care about what they can see. Can they see a human in the dark? Can they see a car against the headlights in the dark? Can you see things outside of the human experience and interpret that? This is very powerful when we talk about the future of AI vision. And in that case, we may want to have a different pattern other than Bayer pattern. Perhaps we have IR, or infrared sensitive pixels, UV sensitive pixels, or multiple different wavelengths that are sensitive, not just red, green, and blue, but maybe 9 or 10 or 20 different filters in front of the pixel to have very narrow slices of wavelength, not only in the visible spectrum, but outside of the visible spectrum. That gives these sort of superpowers to the AI vision systems. Given that we can produce very, very large CMOS sensor arrays, it starts to make sense to put multiple different color filters on top of that and then render that for the AI vision system to interpret. So I predict we'll see many different forms of color filter arrays that are matched to different applications and AI vision systems. So what is a Bayer pattern? Well, it's a color filter array that sits on top of an image sensor in many, many digital still cameras, including the ones in your phone. I believe that Bayer pattern is useful and going to be useful and has a great future, especially if images are used for human consumption. However, I think the landscape is very open when it comes to AI vision and solving new applications, or solving problems and developing new applications with different AI systems. From photons to persons, there is a complete system, and within that system is the opportunity to optimize how the image sensor reacts to the electromagnetic spectrum, not just the visible spectrum, but the IR spectrum, and also slicing and dicing that into finer and finer wavelength components to improve the AI vision system's capability. Well, I hope that helps, and thanks for watching.